Okay. Let's just line this up here. Let's begin. Last time we started talking about vector spaces. So we're still in 4.1. Recall we covered vector spaces, the definition, which is very long to write down, so I'm not going to do that again. But it's something you should be very familiar with. One, pay attention to the definition. That's some things to take away. Don't just think you can just read over it. Something you have to pay attention to. Two, recognize there are three things that are important to define a vector space. Right? So you have to know all the things that will go into defining a vector space. Can anyone tell me what those three things are?
Is it closure and negation?
What?
Exposition.
Hmm? Well, what, when you say closure under addition, what is that? That's one of the vector space what? Right, that list of 10 things, what do we call those? Those were axioms. So I didn't really ask you about the axioms. I'm talking about, to even get to the point where we can talk about the axioms, we first have to have three things in place. What are they? Yeah?
V is a non-empty set of elements.
Right, we need one, we can call it V, but it can be, of course, we name something else, a non-empty set. So before we can even talk about a vector space, we have to have some non-empty set under consideration. What's the second thing we need to have in place? Yeah?
A field.
A field. So I need to be talking about some sort of field, right? The non-empty set, that's where I get our vectors from. The field is where I get my scalars from. And what's the third important thing that's important for a vector space to even start talking about one? Hmm? Hmm?
Zero atoms, operations.
The operations. Right? There are two kinds of operations that we talk about when we're dealing with a vector space. There's addition, and there's scalar multiplication. Right? And again, I put these in quotes because they don't necessarily mean arithmetic addition or scalar or scalar multiplication as you have seen it in Calc 3. This is just a method to combine two vectors. Right? To get another vector. This is just any method that combines a scalar and a vector to make another vector. Right? Of course, the fourth thing in place, which I put a star here, because it's kind of implied once we say we're talking about a vector space, but it must fulfill the 10 axioms. right? That's what's defined, that's what makes it a vector space. So if any one of those 10 things don't work, you're not looking at a vector space. At least not with respect to the other 3. But these 3 must be in place for you to even start talking about this, because the answers can actually change, right? So I can give you an example. Take let V in this notation be R, the real numbers. Let my field F also be R, and let addition and scalar multiplication be the standard arithmetic operation. I think I want to look at here is R plus. This means positive real numbers. Is this a vector space?
No.
The answer is no. Okay, can you tell me why? Huh?
This would be scalar multiplication, because the vector is all real numbers, but greater.
Right. For one, scalar, it's not closed under scalar multiplication. That's one reason, not closed under scalar multiplication. For the second thing, there is no zeros. There is no zero vector here. Third thing, there are no negatives here. We require all of those. So there are a bunch of reasons why this cannot function as a vector space. Because if I take a negative real number times a positive real number, I get a negative real number, I will exit the set. Right? So under these operations, this does not form a vector space. Let's say I tweaked it a little bit. These are the positive numbers. My field F is also the positive numbers. Let's see that. Same operations. Vector space?
No.
Why not?
Does that include zeros?
All right, still no. Because no zero vector. Secondly, I mean, this is kind of an abusive notation, but the positive R's is not a field, so technically I didn't really give you a field, kind of playing unfair here, but at least I wanted to kind of see things that will break down. So that's not a vector space. But let me give you another definition. I'm still going to look at the positive real numbers and the scalars being R. So let's look at the positive real numbers. My field is all the real numbers. But here's how I define addition. U plus V is equal to U times V. So me adding two vectors, I'm using the arithmetic multiplication. And let me define scalar multiplication this way. K times a real number, I'm going to define it to be K raised to that, U raised to that power. Is that a vector space? What does that mean? Yes or no?
Maybe no.
Could be no.
Well, if you say no, it means you know a reason that won't work. What will not work? Yeah?
is v plus u the same, is v times u the same as u times v? Like, well, they're all real numbers, but there's no additional like special algorithm to add.
This is regular multiplication,
Right.
usual multiplication. So yes, it is commutative.
Okay. And u and v as vectors are single elements.
Real numbers, they're
Real
little
numbers,
real
they're
numbers.
not R3.
No, we're in R.
Okay.
But wouldn't it,
Yeah?
There's still no zero?
There's no zero?
But you can make it v, if v is 1, then u plus v is...
There is a zero. The zero vector here is the number 1. Why is that true? So there is a zero.
Technically.
It's u to the k, because you're multiplying them.
What is the definition of zero?
It doesn't
That's
change.
just if you take something and you what am I? If you take something and you add it to that guy, sorry, 0, you get the guy back, right? So if I replace this with the number 1, by definition, that would give me u times 1, which is regular multiplication, so I get u back, right? So so the number 1 actually satisfies the function of 0. Also, by the way, if I take 1 times u, what would I get? I would get u to the 1, which is again u. So number 10 in the vector space axioms is also satisfied. So yes, I do have a 0. Do I have negatives? Are there negatives? Because that would break a vector space.
Yeah.
What are the negatives?
1 over u.
1 over u. In this case, the negative of a vector is 1 over the vector. Do you see why? Because what is the definition of a negative? Right? We say u plus minus u should give us
0.
0. Now, in this case, I know my 0 is 1. So notice that if I take u plus 1 over u, according to this rule of addition, I would end up with u times 1 over u. It actually gives me 1. I do have negatives. Negatives in this case is reciprocal. All right, so when I say pay attention to the definition, this is what I mean. Don't assume you know what 0 means. Don't assume you know what 1 means. It depends on the operations that are defined. So before, positive real numbers was not a vector space in my previous 2 examples, but now it is. Because the set alone is not the only thing that matters. It matters what your field is and what your operations are doing. Right? And in terms of who can get to be a 0, who can get to be a 1, all that stuff depends on the definition of what it means to be a 0 and a 1. So in this case, adding 1 to something didn't change it, so 1 is my 0. And in this case, taking the reciprocal of something is my negative, because by doing that scalar multiplication, I actually get 1 back. Yeah. Yes?
I don't think it meets the... Oh no, maybe it does. Never mind.
Which one? What was it?
The distributive property for multiplication.
So which property are you talking
So
about?
like k times u plus v equals ku plus kv, but I think it actually does, because k wouldn't, it wouldn't,
So
because
that's
scalar
another rule.
multiplication doesn't.
Well, according to our definition, what is this guy?
It would be k squared u to the v, or u to the k,
What? No, what is this guy?
u to the k.
That's u to the k by my definition, plus this would be v to the k, right?
Right.
Now what is this guy?
uv to the k.
This is just k times, my addition is defined as uv, and then that means, what would happen here?
And then distribute that way. So,
And then this would be uv to the k.
which is u to the k times v to the k.
Right, but what is that?
Are they
Because here,
yeah,
this is u to the k times v to the k by that definition.
right.
So they end up being the same. Right, so your vector spaces really depends on three things. There are three things you always have to be paying attention to. It's not just the set that matters, how we're combining elements in the set that matters, who our field is matters. So that's something you really need to pay attention to, and you really need to go by definitions. Because you're going to be dealing with weird spaces where things don't work as they do on the real line normally. Right? Your zero doesn't have to be literally the number zero somewhere. For example, negatives don't have to mean you put a negative sign on something. It could mean take a reciprocal. It could mean something else entirely. Right? It depends on the operation. It turns out that this is a vector space, but I don't know if I ever answered that. But it turns out, yes, this was a vector space. So that the example I just erased, where I did addition was really normal multiplication, and scalar multiplication went to exponentiation. That was a vector space on the positive real numbers. So it's not like, oh, the positive real numbers, we'll never be able to make a vector space because there are no negatives. That's not true. Negative is flexible. Right? I can change what it means to be a negative and make the definition work. Right? So there are a lot of things to pay attention to here. So it's really important that you understand the definitions and not take anything for granted. Right? Zero vector does not mean a vector with all components zero. That's only in Rn with standard operations. Right? It could mean something else. Let's do some more examples. I gave you the example of a color map, which was not a vector space. Let's see. Here are some ones that you should kind of know. So basically Rn with standard operations. Over R is a vector space. And Rn is just a generic term that refers to any of the Euclidean n spaces. So that would include R itself, R2, R3. These are the guys you dealt with in Calc 3, but you can generalize that to fourth dimensional space and beyond. Right? Any set of finite number of vector spaces. This guy would just be a vector with 4 components. Right? So Rn, how you look at that, that's just the set of all vectors such that my vector looks like x1, comma x2, comma all the way up to xn, where the xi's are real numbers. And such a space with the usual vector addition that you learned from Calc 3, those will always be vector space. They will always fulfill those 10 conditions. So those are just some standard ones that you should be aware of. Here's another example. The set of n by n matrices is a vector space over R with matrix addition and scalar multiplication. So the zero vector there is just going to be the matrix with 0 in all its entries. Negatives are just, you may take the negative of each entry. You realize if you add 2 matrices of a certain size, you get another matrix of that size. And if you take a scalar multiple of a matrix of a certain size, you get another multiple of a certain size. And the properties that I gave you in the handout tells you that all the other 10 properties actually work. So that is an example of a vector space. So I can say the set of all 2 by 3 matrices, that is a vector space with matrix addition and matrix scalar multiplication. Right? And yes, scalar multiplication, not matrix multiplication. Notice that in my definitions of a vector space, I do not know what it means to multiply two vectors, right? I only know what it means to add two vectors and what it means to multiply a scalar by a vector. Notice that multiplication between vectors is not defined. All right, so once you start defining multiplication between vectors, you're not a vector space anymore, you're something else. You could be a ring or a field or something similar. But for vector spaces, you don't care about multiplication between vectors. Other nice examples. Oh, here's a common one. Well, it's appropriately named the trivial vector space because it's trivial in most cases and we don't even consider it. But technically it fulfills all the axioms, right? Or it's sometimes referred to as the zero vector space. And this is just when V is literally just the zero set. The set containing zero. Pretty much with any operation, that's why it's kind of trivial. We'll see that later. We'll do a theorem where you can see why that would always be true. The truth is because by the definition of zero, if I multiply that by any scalar, I will have to get zero. The only possible things to add together is zero with itself, but by the definition of zero, that will always give us zero. All the things would work out, all the 10 theorems will work out. So there's an example of the trivial vector space, or the zero vector space. It's literally a vector space on a set that only has one element in it, namely the zero vector. That fulfills the 10 property. Another vector space. Anyone give me some common ones, maybe in terms of things that we've seen before? For previous math classes, what, looking back, can we think of as vector spaces? The set of
Projections?
Set of projections is a vector space? Well, you'd have to define the operations there. It's a little too complicated. Let's make something simpler. That would be a nice example to do when I cover like transformations of functions, transformations of matrices. Something even a little nicer. Yeah?
Graphs, so edges and nodes, and the connections between them could be mapped as a
Gradient?
vector space.
Gradient?
Like edges and graphs?
Yeah.
Like you've seen that in previous classes? Like who here has done graphs theory?
I just looked that up.
That is true. Yeah?
Set of complex numbers?
Yes, set of complex numbers is a vector space over R, so Cn. Right, so this is just basically, if you have a vector, set of all vectors that have components like z1, comma z2, comma z3, comma all the way up to zn, such that zi is a complex number, meaning it looks like a plus ib. That is also a vector space? Sure, with the standard operations. Anything else? With standard operations. That means complex addition, complex number multiplication, which follows the distributive law. Here's something you might not have thought of. Pn. This is the set of polynomials of degree less than or equal to n, with function addition and scalar multiplication. Is a vector space. So I can think of P2, for example. Right? P2, for example, the set of all polynomials that are quadratics or linear or constant. If I add any two such polynomials, I get one of those polynomials. If I multiply any of those guys by a scalar, I get such a polynomial. I can add them and do all sorts of things. The distributive law holds, all that holds. There's something f from minus infinity to infinity. This is the set of all functions continuous, set of all functions on minus infinity to infinity with function addition that is a vector space, usual operations. There are examples like so all of these, I'm going to describe them because they're very similar. With the usual operations, meaning like from you would have done in previous classes. Following are vector spaces over R. This is a set of all continuous functions on the real line. There's also the set C1. Those of you who are math majors will start to see these guys all over the place all the time. This is a set of once differentiable continuous functions. And you can have all sorts of these guys. In general, you can talk about Cn. This is the set of nth differentiable functions. Right, so functions that we can differentiate n times and they're continuous on the real line. Which I mean, in calculus you wouldn't have seen many functions that are not like that. But there are examples. Example of a function that is C1 but not C2. It's something like this function. That's a function that you can differentiate once and no more. Other examples. So I spoke about matrices already, I think. I'm really just powering through examples here. I really want you guys to go over and look over all these things and try to justify to yourselves why. What other example do I have? Here's another example. Take V to be the set of 2 by 2 matrices with, say, A, B, C, D plus E, F, G, H equals A plus E plus 1, B plus F plus 1, C plus G plus 1, D plus H plus 1. So I redefined it in addition to add an extra 1. And scalar times A, B, C, D is equal to just the regular scalar multiplication. This is a vector space. Right? Well, everything that has to do with scalar multiplication is going to be exactly the same. But in terms of addition, clearly this is close. I add two 2x2 matrices, I get another 2x2 matrix, and we can go through all of that. Who is the zero vector here? Yeah.
-1, -1.
The zero vector is just going to be the matrix with all negative ones, as opposed to all zeros. Right? But with that zero, that forms a vector space. So you can do all sorts of tweaks here. And in your homework, there'll be tons more, especially if you look at the suggested problems, there'll be tons more examples of vector spaces. I don't know. I'm yet beating this to death. Sure, vector space. I told you about the exclusive OR and AND gates vector space. That was the one on Z2 where 1 plus 1 was equal to 1, 1 plus 0 was equal to 1, all that stuff. In that example that I gave last time, you can think of 1 as true and 0 as false, or 1 as on and 0 as off. And those sets of equations that I gave you, they would sort of make sense. Here's a fun example. I'm not sure exactly how this would apply, but the set of nth order magic squares. With matrix addition and scalar multiplication. So magic square, by the way, the nth magic square is a matrix with entries with distinct entries so that every row, column, and the main diagonal sums to the same number. By that definition, you will of course know that there is no 2 by 2 magic square, but there is a 3 by 3 magic square. Usually you go from 1 up to the order. So here's an example of one. So I don't have to 8, 1, 6, 3, 5, 7, 4, 9, 2. Look at that square. Sort of think of it as a Sudoku puzzle. You have to fill in all the numbers. But you add the constraint that if you add any row or any column or the main diagonal, you need to get the same number, or any diagonal, you get the same number. You'll notice that all of these guys add to 15. You sum to 15. Turns out there's only one 3 by 3 magic square, because every other magic square that you can make of this size is just going to be a rotation of this one. And that's sort of some interesting examples in abstract algebra. The famous mathematician Ramanujan was enamored with these for a while. Because they can get quite complicated. Like there's only one 3 by 3 magic square, but if you look at 4 by 4s, suddenly it jumps to like there's 800 possible ones, and then you jump to 5 by 5s, there's like 200 million of those, and it's like, what's the pattern? Like how did, you know, number theorists, they have fun with things like that. Did anyone come up with an interesting real life example? I think it's really tough to come up with those. Like I couldn't really come up with a nice one. The closest I could get was that AND gate. But okay. So if you can't really come up with a real life example, what's the point of studying linear algebra? But we'll see what that point is. one thing you can know is that if you consider Rn as a vector space, we'll talk about the subspaces of Rn. Those guys are planes, and we know that if we can find planes, we can approximate complicated things. So even though when directly we won't have things looking like that, we can use it to approximate things that look like that. And there are all sorts of things that in computers will work out. So when you're really looking at math that would describe physical reality, calculus is really the best thing you have going for you. But more in like computer science, then discrete math and linear algebra actually work out better. Just because of how things set up. The computer world is a very discrete world. Calculus doesn't really work. And so you need another kind of math to do stuff there, and linear algebra ends up being a nice one. For those of you who have taken differential equations, another example is, again, with the usual operations. The set of solutions to the ODE. Take some second order ODE. And look at all its possible solutions. They form a vector space. In fact, that's true for nth order ODEs, and that's why in differential equation you always had n solutions to an nth order differential equation. We'll see why that is when we start to look at it from a vector space perspective. You'll have C1y1 plus C2y2. Why? Because it's a two-dimensional vector space. You have to have two solutions for a two-dimensional vector space. And if you have a third order, it's a three-dimensional vector space. You have to have three solutions for a three-dimensional vector space, etc. Right? It's kind of like when you're looking at a system of equations, your answer is a vector that has as many coordinates as there are variables. It's sort of the same thing. Let's look at an important theorem, because I'm tired of listing examples. But there are tons of examples in the math world for vector spaces. So you'll see a lot more in your homework and in the practice problems and all that. But let's actually prove a nice theorem. Let V be, I also would mention, I can mention that. Let V be a vector space. And assume the vectors U and V are in V, and K is a scalar in R. Then, I want to make a note about the fact that we're pretty much always going to be using R. The following are true. Now some of these would seem painfully obvious with me writing them down, but you have to remember, we assume nothing. Because these vectors here, they might not be vectors in Rn. They can be some other kind of thing that doesn't work the same way that Rn works. And so we have to make sure that this is always true. It turns out that they are, thankfully, because that's very intuitive. Notice here, in this class, we will usually use, the field would usually be the real numbers. So unless otherwise stated, it's always going to be the real numbers. The 99% of my examples, I'll be using that as the field. But it's very common to also use complex numbers and other things, but we're only going to look at R. So let's look at R. So what I'm going to do is I'm going to prove the first part, and you guys are going to help me prove the others. How do I know that the scalar 0 times a vector gives me the 0 vector? Does anyone have any idea how to prove this? Yes.
Haven't we seen that if you redefine addition, then that's not always the case, though? Like, if we had that vector space where the zero vector was -1, -1, -1,
What would be wrong in that case?
well, like, because then the scalar 0 times whatever vector wouldn't give us -1, -1, -1. -1, it would give us 0, 0, 0, 0.
Oh, we'd have to change scalar multiplication.
Okay.
Yep. You're talking about that matrix where I put the +1 on it?
Yeah, the way you.
Okay. Let's see, why is this always true? Here's one way. If the 0 doesn't have a vector over it, it means you can think of it as the real number 0, right? That scalar is just from R. Right, so it's just the real number 0. So it turns out that anything I can do with the real number 0, I can do with this 0. So the trick goes something like this. 0 is actually the same as 0 plus 0. Which looks like cheating, but that's the standard thing to do. When you're completing the square, you kind of add and subtract 0 in a convenient way, and all that sort of stuff. So that's true, right? And now, according to our vector space axioms, what does something like this become?
0u plus 0u?
0u plus 0u. This happens by a vector axiom. This is just a property of 0 in R. Okay, so what can we say now? This means I can immediately say this. Why?
You can subtract everybody.
That is a zero vector.
Yeah, why can we say that's a 0 vector?
Axiom A.
Huh?
Axiom A over there?
Axiom A is what I want to prove, so no, I can't say that.
Isn't that the definition of the zero vector?
Yeah, what's the definition of 0 vector?
Elements that are zero?
No,
Like-
that's not the,
Oh, in vector space.
in vector space. Yeah?
Because when you add it, it gave you the same thing. So treat one of them as.
Yeah, so this is by axiom 4. So if you look at axiom 4, that defines the 0 vector. What is 0? So when you add 0 to something, what should you get? The same thing. So notice here, I have this guy, and I added something, and I got the same thing. Which means that that thing that I added, I can think of that as the 0. Right? Falls from the definition. Okay, so that's the proof for that. I know it seems a little seems like cheating, but it's not. This follows by the property of the real numbers. This follows by the vector axiom that says a scalar, I can distribute scalars across a vector. And this follows by literally the definition of what it means to be the 0 vector. What about B? So I've done that, so maybe you can do this one. How would you prove that k times 0 is the 0 vector? It's actually using a very similar trick formula. So I'll start with the one side, k times 0.
Wouldn't it be like k times 0 plus 0?
I think that would be the nicer way to do it. K times 0 plus 0. This happens by definition of 0. I can write any vector as itself plus the 0 vector because it just gives me that vector. So that's true by the definition of 0. Then I can, again, distribute this. Again, that's by axiom I forget what number axiom that is. I think I defined 0 as axiom 4, and then the distributive law was one of the axioms. And so this means that k times 0 is actually 0, because this is a number. If I take something and I add 0 to it, it makes no difference. I get the original thing back. What about part C? How would I prove that if I take negative 1 times u, that I get, that's by definition the negative of u?
Wouldn't that be like 1 over u?
No.
Would it be kind of like the same reason we get the 0, kind of looking at it as a real number, the negative 1?
Okay, but how would you, how would you go
0
about it?
minus 1. Split it into 0 minus 1 and then distribute.
Okay. So
That's
if
what
I
I'm
have
doing.
minus 1 times u, you would say that is 0 minus 1?
Sure. Going by the pattern.
Okay, and then what could you say here?
Minus u equals to 0 u minus 1 u?
0 u, yeah, 0 u minus 1 u equals negative 1 u. And 0 u we've already proven.
Yeah, but that, you would just get 0 here.
Right.
You'd end up with literally the same thing. So, not quite. But you're thinking along the same lines. Probably especially since all the vector space axioms, they have all pluses. You probably want to think in terms of pluses as opposed to thinking in terms of minuses. By the way, what does it mean to be negative u? Let's start there.
Going in the opposite direction. Like if we're thinking about
It means
vectors,
if I take the original and add this guy, I get the 0 vector, right? That's what it means. So in other words, what I want to prove is that if I take this guy and I add this guy, I get 0. And so this would satisfy the definition of that. But if I start out, let's look at this guy, which is where we want to start and we want to end here. What can I do with this? I can factor out the u, right? So note that if I take u plus, I add minus 1 times u, I can actually factor out the u on the right side, and that would give me 1 plus a minus 1. Now remember, in here we're in the real numbers. So that's just 0 times u. But this is equal to the 0 vector by part A. And so that means minus 1 times u is the negative of u. It is the vector that if I add to this, I get 0. How about the last one? That one's a bit tricky. If k times u is the 0 vector, then either k is the real number 0 or u is the 0 vector with respect to the vector space axiom.
Could we do like k times the u vector plus the 0 vector in parentheses to distribute?
What would you distribute there? If you take k times the u vector plus the 0 vector?
In parentheses.
Okay.
No, outside the, it would be k u plus the 0 vector. In
Oh,
parentheses.
you're saying k times u and then you add the 0 vector like that?
Yeah. Which would equal to the 0 vector.
which would equal to? Well, we don't know it's equal to the zero vector, but what are you trying to say?
Okay, if we redistribute this, we would get k to the u vector plus k to the zero vector.
So this is you rewriting k times u, right? So you took k times u, you replace u with u plus the zero vector, then you distribute, and so what does that mean? That would basically mean that this is true, right?
Yeah.
But that's not what we want to prove, so. Yeah?
Can you do this by contradiction in cases?
Contradiction. Notice that we have an implication where we have an if then, right? So it's like an if P then Q. So what are our options here? Right? You can do direct proof, proof by contrapositive, proof by contradiction, all that stuff. So you want to do by contradiction?
Yes.
Okay. So what does that mean you assume? Assume to the contrary that
K U is not equal to 0.
no, that's not how
K and
contradiction.
U is equal to
Then
0.
neither is equal to 0.
What do you mean?
K U is not equal to 0.
No.
K is equal to 0 and K is not equal to 0.
Remember when we're doing contradiction, how is the setup for that? If you want to prove P implies Q, what do you assume for contradiction?
P implies negation of Q.
Not P,
Assume not Q
No, that's contrapositive.
What do we assume, not P or not Q?
No. Yeah? No, tell me the general principle. If I want to prove P implies Q and I want to do contradiction, what is my assumption? Where do I start?
Q.
What if both of them are 0?
Not P implies Q.
Huh?
Is it just not P implies Q?
No.
Don't you just assume that the negation of Q is true?
So not P implies Q implies that K or U.
You guys have to review contradiction. You assume P and not Q. That's what you assume for contradiction. So you're going to assume the first statement is true, but the second statement is false. That's how contradiction starts. So what I'm going to do is I'm going to assume that K times U does give me the 0, but what's the opposite of this? What's the negation of either K is 0 or U is the 0 vector?
K is not 0.
K is not 0 and U is not the 0 vector. Right? So I said either or needs to be true. I'm saying no, assume that's false. Assume that they're both false. Right? So it's not one or the other. It's true, they're both false. So assume that the first statement is true, but this statement is false, means I'm assuming that. So what can I do with that? So I know that this is true, but that's not. I want to obtain a contradiction. Where do we go from here? Yeah?
I mean, KU plus negative KU would have to equal the 0 vector if they're not 0 themselves.
Okay.
But that's, I don't see how that would
We know, because we're assuming here, that K times U is equal to 0. So, if K is not equal to 0, what could I do here?
divide K on.
I can divide by K. In other words, K inverse exists, which means, which is the reciprocal, right? But I sort of want you guys to get away from thinking in terms of division. So let's write it like that, right? So this would mean that U is equal to K inverse times 0. Now, by definition, this, what is this guy? What is a scalar times the 0 vector?
0.
That's the 0 vector. By, we actually proved that as one of the parts. By part B. And that's my contradiction, because I said U was not the 0 vector. But then I obtained that U has to be the 0 vector.
Do you have to do both?
Hmm?
Do you have to then prove it the other way that
No,
K
I've obtained a contradiction. That's how proof by contradiction works. I make this assumption, and if anything breaks, I don't care how many things break, if any one thing breaks, I've proven it. So a vector space is a set over a field with two operations that fulfill those 10 conditions. I gave you many examples, and we just proved this theorem. So now any of these facts you can use at will, unless I specifically ask you to prove one of these facts. So from now on you can use these facts, right? Like 0 times a vector is the 0 vector and all that stuff. These are things you can use now in the future. Let's get started on this guy, subspaces. And this is a really long section, so we'll only get it started. I'm going to start with a definition. Let V be a vector space. And by the way, I'll just say that, but you should be able to assume that, okay, there's a field and there are two operations here, and together they all make a vector space, right? But, so once I say let V be a vector space, it implies all that. And then let U be a subset of V. Right? So U contains some or possibly all of the elements of V. Then we call U a subspace of V if it is itself a vector space with respect to the operations defined on V. That's the definition of a subspace. So here I have my set V. It's doing whatever. I know that this is a vector space. If I take some subspace inside of this thing, which I call U, and if this is a vector space, then I call it a subspace. It's a subset of the set that is also a vector space if I use the same operations. Not all subsets are vector spaces, only particular ones. I'll give you a theorem that tells you when you will have a subspace, and you can, some people use this as an equivalent definition. Theorem. Let V be a vector space. And U be a subset of V. Then U is a subspace if and only if two conditions hold. One, U is closed under addition as defined for V. And two, U is closed under scalar multiplication. As defined for V. So if you have a subset that is closed under addition and scalar multiplication, you will have created another vector space, a baby vector space, inside a larger vector space. Notice this is an if and only if. So there are two directions to prove. The direction moving in this way is pretty much easy. If U is a subspace, then it is a vector space. So it fulfills the 10 axioms. Which of course include 1 and 2. So if it's a subspace, of course it fulfills those two. Those are part of what makes something a vector space. Conversely, let's prove the other direction. Conversely, suppose U is a subset closed under addition and scalar multiplication. I need to prove that it's a vector space. So note, U has a zero vector since by the previous theorem, if I take 0 times U, I would get the zero vector for U in U. Right? So take any element in my subset. If I multiply it by the real number 0, I would get the zero vector by that theorem. So that, but since it's closed under scalar multiplication, this is in that set. So since U is closed under scalar multiplication, 0 times U equals 0 is an element of U. Also, minus 1 times U will equal to the negative of U by previous theorem. And so U contains negatives. Turns out those were the two hardest things to prove. All other axioms follow for free, right? Because I'm using the same operations on V, and these are elements of V, so all those operations automatically work, right? Because everything in U is an element in V, and we know that all these operations work in V, so they'll have to work in U. The only thing that we're not sure about is the existence of a zero vector and the existence of negatives. these are the only two things that they don't purely deal with the operations, but they deal with something that you have to find. You have to locate. Okay, is this guy around here? And those two guys are. Everything else will follow for free because when you add two things, you can get another thing. And so we'll stop there. I'll give you examples of subspaces next time. So technically, none of this will be on the test unless I probably put it in a bonus problem or something. So we finished the test on everything that's before chapter 4, and our test is on Tuesday. So make sure you go over the review, look over it this weekend. You can email me if you have any questions, and you can meet with me on Monday if you think you need to clarify. We'll stop there.